Okay, finally, let's talk about some advantages and maybe disadvantages or limitations of this particular numerical lifting line algorithm. So first, let's start with the advantages over here. So, advantage of using this over other methods is that it is fast. So if you can compare this to full CFD, this is order of magnitudes faster than CFD. It can even be an order of magnitude faster than other panel codes. So if you're familiar with codes like Panair, even low order or high order panel codes, this can be significantly faster than those and still give reasonable solutions. Okay. Another advantage is that it can handle interactions between lifting surfaces. So that means that it can estimate or account for the downwash on the horizontal tail from the main wing or the upwash on a canard forward of the main wing. So it's capturing all of these interactions simultaneously. You put all of these wings into the algorithm at the same time, and you get the interaction between all of these simultaneously. So anyway, that's a nice advantage of the tool or this method. And then next, it gives relatively accurate solutions for many designs. Okay, so I'm going to say relatively accurate for many designs, and we're going to talk about some of the limitations here in just a minute. But for a lot of aircraft design, it gives a pretty good first cut at the aerodynamics of the lifting surfaces. And now it neglects the fuselage and some other things we'll talk about here in a second. But just if you're just looking at the aerodynamics of the lifting surfaces themselves, it's pretty good. And then finally, it can handle actually fairly complex geometries. So for example, you can have nonlinear sweep, dihedral, airfoil properties. You can capture a lot of nonlinearity in using this model. So for example, let me just give you an idea of nonlinear dihedral is maybe dihedral that changes as it goes out, or sweep that changes as it goes out. You can capture this nonlinear aerodynamics to a certain extent. You can account for viscous drag. And actually, I'll just add that as another one. So nonlinear aerodynamics and viscous effects. Okay, so it's a pretty solid method for a pretty large range of wing designs or aircraft designs that you might want to consider. Okay, however, it has some fairly significant limitations, and so let's talk about that over here. First of all, this is inherently a potential flow method. Okay, so that already just the fact that it has that its potential flow already offers some limitations compared to CFD or experiment, where we're going to be neglecting things. We just are, by the nature of the equations that we've developed. We've thrown away some the effects of viscosity and in order to simplify the solutions down to this potential flow method. So anyway, that's just baked in. This is also not very accurate for low aspect ratio wings. Okay, so you can think about one of the main assumptions that is built into this is that the vorticity that would be distributed along an airfoil is all coalesced at the quarter chord, where we're placing this lifting line. And so if you look at this cross section of a wing, and we're placing all of this vorticity here at that location, gamma. It can't account for these chordwise effects. Actually that vorticity is distributed along the airfoil, and we're lumping it all there at the quarter chord. And so that's more accurate for higher aspect ratio wings. So it turns out that that for aspect ratios less than 4, you want to be a bit skeptical of the results. For aspect ratios greater than 4, it actually gives fairly reasonable results. So that's actually a lower aspect ratio than you would probably expect, given this this type of assumption that's built into it. So most aircraft, their main wing has an aspect ratio closer to 8 or 12. However, if you're going to use this for the horizontal stabilizer, the vertical stabilizer, now you're getting into lower aspect ratio wings. And certainly when you get to fighter aircraft, those have very low aspect ratio wings. And so just the accuracy of the method breaks down for those low aspect ratio wing designs. Okay, another thing we already mentioned, I'll just write it down, is that it does not include any effects of the fuselage. So that, that some might argue is more of a secondary effect. It really depends on the design of your fuselage. And anyway, it's just completely neglected in this theory. And then finally, I want to kind of focus on this last drawback. When Phillips and Snyder published this, they said that this algorithm could be used for wings with sweep and dihedral. I'm just going to write that down here. Sweep and dihedral. And I don't know if they explicitly stated it, but they also kind of imply, I guess, or you can assume that it would also be good for wings in side slip. Okay, so and they published some results. They even showed results for a wing with sweep. They showed it, I think it was the lift slope of the wing as a function of sweep angle or something like that, and that it seemed to be matching other prediction methods, CFD and panel methods, and possibly experimental data. I can't remember exactly what they showed, but in general, they showed that for sweep it was giving fairly decent integrated results. However, if you look at the lift distribution on the wing, there's a couple things I want to point out. So let's take a wing that has some sweep here, and we're placing our bound vorticity along the quarter chord. If you look at the lift distribution that comes out of this solution, it will look something like this. Okay, well, we're actually going to see that the vorticity, or the lift, goes to 0 right there at the center of this wing. Now, the fact that the vorticity drops, or the lift drops in the center of the section, or the wing, if you have sweep, is a well-known phenomenon. In fact, I believe the Horton brothers called it the Mittel effect in German, and in English, obviously, middle effect. But basically, they found that you do get a drop in lift there near the center line. And actually, we understand really well why that's happening. It's because the bound vorticity here along one wing is at an angle to the bound vorticity on the other side. And remember that the influence goes up as 1 over r squared, I believe, as your distance decreases, or actually it drops off as 1 over r squared as your distance increases. And so as we get closer to this center section, these regions of bound vorticity are heavily influencing the bound vorticity or the angle of attack on the other side of the wing. This region out here, the angle that makes to a region over here, or really anywhere along the wing, that the influence of this bound vorticity on points along on the other side of the wing is pretty small. But as you get close to this discontinuity here in the center, you have bound vorticity at an angle, and that creates downwash on the opposite side of the wing. And so you can kind of imagine that both of the wings are flying in each other's downwash. That's one way to think of it. You're getting downwash from the velocity induced like that, and as you get close to the center, you have a lot of downwash, and so your angle of attack or your lift drops basically to 0 there at that point. Anyway, or decreases, I guess I should say. So that is a real thing, that your lift is going to decrease in the center, but this particular algorithm says that it goes to 0, and that is exaggerated. That's not really true. And because it exaggerates that, it also exaggerates your induced drag in this region, because your induced drag is related to the gradient of your lift, and so you have a higher induced drag in the center than maybe would be real. So Anyway, so this is one of the drawbacks, and you get a similar type of behavior with dihedral. Okay, so sweep and dihedral will both do something like this. And then, but there's actually one other thing that we need to understand about sweep, dihedral, and side slip that is perhaps even more bothersome, and that is that if you have sweep, dihedral, or side slip, this method does not converge. Does not converge. And by that, I mean it does not grid converge, okay, or grid resolve, meaning that as you double the grid, you do not approach some value. So let's talk about grid convergence here for just a second. Let's say that we have the number of nodes that we've used in our simulation here on the x-axis, and then the total lift coefficient on the swing on the y-axis. So let's say I use 20 nodes on this, and I get some lift coefficient here, okay? And then if this were a straight wing, and I doubled the number of nodes, so we'll go to 40 nodes, and I get a slightly different answer. Well, as I increase the grid resolution, I would expect this to level off at some value, and so we can estimate what that is. There's actually a method called Richardson extrapolation, where if we have 3 solutions along this curve, we can extrapolate what that, where this solution is going out at n equals infinity. Okay, if I had an infinite number of nodes, and if that looks like this, if it offers that kind of behavior, then we would call that a convergent solution, and the rate at which that converges is the order of convergence. Okay, so anyway, that's what happens for a straight wing. Well, once we sweep the wing, it turns out that our solution doesn't really converge, and so it will just continue to march in a direction as we refine the grid. And so we can really get any solution we want. We can get any lift coefficient we want just by choosing the number of grid points that we're using in this simulation. So that's not a good numerical algorithm. If it doesn't grid resolve, then you don't trust it. And Phillips and Snyder didn't realize this when they published the paper. They actually did think that it grid resolved, but you can code it up yourself. I've coded it up. I've had others code it up, and we have in fact shown that this does not grid resolve once you have sweep, dihedral, or side slip. Okay. So even if you have a straight wing, if you have side slip, it still doesn't even grid resolve. So anyway, these are pretty significant limitations. Before we throw up our hands and say all is lost, I just want to mention that there's a paper by Jackson Reed, and again I'll put this a link in the description down here. But this paper talks about how to modify this original numerical method by Phillips and Snyder in order to accurately to get a system of equations that does grid resolve. And he digs into the mathematics of what is causing this method to not grid resolve, and is able to come up with solutions for managing that. And he actually comes up with an algorithm that works really quite well for swept wings, and wings and side slip. So anyway, I'd recommend, if you're really interested in this algorithm, it's a fantastic algorithm for many applications. But if you are going to use sweep, dihedral, or side slip, then you may want to look into Jackson Reed's corrections to this algorithm, I should say, or modifications that get rid of that major drawback of using this particular algorithm.